People are strange when you're a stranger. Faces look ugly when you're alone.
The goal of the rest of this lecture is to show that the nth cyclotomic polynomial has integer coefficients and is irreducible. But we're going to start with a question that we're going to try to understand first that will help us along the way, which is, how do we figure out what the nth cyclotomic polynomial is? Like, how would we check those statements for a particular value of n? Well, we know that x to the n minus 1 has roots equal to the nth roots of unity. So we can factor this in q adjoins zeta n bracket x as a product over all zeta in mu n of x minus zeta. And then this is equal to a product over all divisors d of n of the product of x minus zeta, where now zeta goes through just the primitive dth roots of unity. So this step is important, so I want to highlight what's going on here. Is here we have this finite cyclic group of order n, mu n, and we're going to group together the linear factors corresponding to elements of order exactly d in mu n. So that means that we're taking exactly the elements inside of mu n that are actually dth roots of unity and are primitive dth roots of unity. So it's a product over d dividing n of these x minus zetas, where zeta goes through the primitive dth roots of unity. But we know a polynomial whose roots are the primitive dth roots of unity. That is the dth cyclotomic polynomial phi d of x. So x to the n minus 1 factors as a product over divisors d of n of the dth cyclotomic polynomial. So I just want to point out now, we have this equality that really came from comparing roots on both sides. And if you compare the degrees, you'll see that the degree of the left-hand side is n. And the degree of the right-hand side, well, the degree of a product is the sum of the degrees. And the degree of the dth cyclotomic polynomial is phi d. So we get n is equal to a sum over divisors d of n of the Euler phi function phi of d. And I'll point out that we already proved this in Math 206b, lecture 11, video 3. This was part of the second proof that we gave that the multiplicative group of a finite field is cyclic. So I encourage you to look back at that argument, and you can compare how these relate. Okay, so what's the idea? We're going to compute the nth cyclotomic polynomial by using this factorization of x to the n minus 1 is a product of all d dividing n of phi d of x. So if we know phi d of x for all d less than n, then we can just divide, and we can get our phi n of x term on the right-hand side. So for example, when n is prime, p, x to the p minus 1 is the first cyclotomic polynomial times the pth cyclotomic polynomial. And the first cyclotomic polynomial, okay, what is that? That's the polynomial whose roots are the primitive first roots of unity. But there's only one first root of unity, which is 1. So this polynomial is x minus 1. So x to the p minus 1 equals x minus 1 times whatever this is. So whatever this is, the pth cyclotomic polynomial is the quotient x to the p minus 1 divided by x minus 1, which is x to the p minus 1 plus x to the p minus 2 plus x plus 1. So this is a polynomial that we first talked about back in Math 206b, and we just defined it this way. But now we're really seeing why the pth cyclotomic polynomial, the polynomial whose roots are the primitive pth roots of unity, is x to the p minus 1 plus x to the p minus 2 plus x plus 1. All right, so now let's look at some exponents that are not prime. X to the 6 minus 1. That's phi 1 of x times phi 2 of x times phi 3 of x times phi 6 of x. We go over all the divisors of 6, and we can see what each of them are, because we already know the first cyclotomic polynomial is x minus 1. And then 2 and 3 are prime, so we can use this fact here and see that we get x minus 1 times x plus 1 times x squared plus x plus 1 times whatever phi 6 of x is. Long division shows us that this is x squared minus x plus 1. And you can check that that's true. 4, that's not a prime. So let's take x to the 4th minus 1. This is the product of the first cyclotomic polynomial, the second cyclotomic polynomial, and the fourth cyclotomic polynomial, we know that phi1 times phi2 is x squared minus 1. So divide and you get the fourth cyclotomic polynomial is x to the fourth minus 1 over x squared minus 1. And that's just x squared plus 1. And if you think about it, what are the roots of this polynomial? Say in C, it's x minus I and x plus I, which are the two primitive fourth roots of unity in C. So this factors further in the complex numbers. This is irreducible over Q, but factors further in C. So you can continue in this way and start to look for patterns. For example, exercise 6 in section 13.6 says for n larger than 1 odd, the 2nth cyclotomic polynomial is the nth cyclotomic polynomial of negative x. You put in a negative x everywhere you see x. So what's the difference between phi n of negative x and phi n of x is every time you have an odd exponent, you take the negative of the corresponding coefficient. Okay, so you can think about how to prove this by comparing the set of primitive 2nth roots of unity with the set of primitive nth roots of unity. Or more generally, how do the 2nth roots of unity and the nth roots of unity compare? Okay, so far, all the examples we've seen have integer coefficients. And the main goal of this video is to prove that the nth cyclotomic polynomial has integer coefficients for every n. But so far, in fact, something much stronger is true, that all of the cyclotomic polynomials we've seen have coefficients that are 1, -1, or 0. So this is not true in general for the nth cyclotomic polynomial. And when I was an undergraduate, I did an REU project about coefficients of cyclotomic polynomials. So I'm going to pause and erase and just say a little bit about some of these questions about these coefficients. We know that if p is prime, the pth cyclotomic polynomial is x to the p minus 1 plus x to the p minus 2 plus x plus 1. And you could say, okay, well, when n is prime, that's the easiest case to understand all of the coefficients of the nth cyclotomic polynomial. What if you have a product of 2 primes? And it's a fact that if p less than q are primes, every coefficient of the pqth cyclotomic polynomial is in the set 1, -1, or 0. If you go back, you'll see that this is true, for example, for the 6th cyclotomic polynomial. So this is something you could try to prove for yourself. It's a little bit tricky, but I encourage you to think about it. But this result is well known. So you could ask, what happens when you go from products of 2 primes to products of 3 primes? And here, if you take 105, which is 3 times 5 times 7, and you look at the 105th cyclotomic polynomial, you'll see that the x to the 7 coefficient is equal to -2. So it's no longer true, once you have products of 3 or more primes, that all of the coefficients are 1, -1, or 0. So it's a natural question to ask, well, if the coefficients no longer just have to be 1, -1, or 0, how big can they get? So here's a question. Let's say that p less than q less than r are odd primes. You could say, what is the largest that the absolute value of a coefficient of the pqr cyclotomic polynomial can be? For example, for 105, this has one coefficient equal to -2, but no coefficient is bigger than 2 in absolute value. So it is known, it has been known for a very long time, that you can give a bound on these coefficients, the absolute value of these coefficients, that only depends on p. That you pick p to be whatever it is. Q and r can be any gigantic primes, and you can give a bound on these coefficients only in terms of p. So this summer project that I did on cyclotomic polynomial coefficients, one thing I thought a lot about was this conjecture from the late 1960s of Beater that said that the largest that the absolute value of a coefficient of this polynomial can be is p plus 1 divided by 2. Okay, just as a check, here, 3 times 5 times 7, 3 plus 1 divided by 2 is 2. So that matches up with this minus 2 here. And in fact, during this summer project, I got so excited. I thought I had proven this conjecture that at the time was almost 40 years old. And I was like, oh, I'm the best undergrad ever. This is so awesome. My proof turned out not to work. And maybe the main reason that the argument didn't work is that this conjecture was false. So it turned out to be false. And the first counterexample is when P, Q, and R are 17, 29, and 41. So that was well within the range of examples I could have just looked at with Mathematica. So I should have. That's how I was checking examples at the time. And I take this story as like a little reminder that before trying too hard to prove that something is true, you should probably check that it actually really is true. It turns out there's this whole interesting story about, okay, so that original conjecture was not true. How do you give a modified version of this conjecture that is true? So replace this function p plus 1 over 2 with some other function that really does hold as an upper bound that only depends on p. And there's this very interesting work of Murray and Gallo and others that answers this question. Okay, so notice that in talking about these examples, I said p less than q are primes. So we didn't look at, for example, the p squared cyclotomic polynomial. We did see one example of that earlier in this video when we did the fourth cyclotomic polynomial is x squared plus 1. So one question that is easier that you really might want to think about, you don't have to, but if you want to think about this kind of thing, you could say, okay, suppose that p divides n. What is the p times nth cyclotomic polynomial in terms of the nth cyclotomic polynomial? How do the p times nth roots of unity compare to the nth roots of unity? And answering this question is a little bit easier than proving this fact. And then these types of questions, once you have 3 or more primes dividing n, get really pretty complicated. For the reason on the previous slide, this relationship about the 2nth cyclotomic polynomial and the nth cyclotomic polynomial when n is odd, really we would focus on the case of products of odd primes. Okay, so you don't need to know any of this for the rest of this course, but I just wanted to tell you like some of these kinds of questions that people have thought about before. I'll end this little interlude with one more. Here, we're taking products of 3 odd primes, and we're saying that we want the absolute value of the coefficients to be as large as possible, some coefficient. But you could also ask a question like, can I come up with families of examples of p, q, and r where it turns out that all of the coefficients of the pqrth cyclotomic polynomial do lie in the set 1 minus 1 or 0. So that's actually something I thought about a lot in this research project. Here's something that's not known. Does there exist an n that is a product of 5 or more odd primes, distinct odd primes, for which the nth cyclotomic polynomial has all of its coefficients in the set 1, minus 1, or 0? Okay, so for 4 odd primes, we know infinitely many examples. But for 5 or more odd primes, we don't know any examples at all. Okay, so now you can forget about all that. We're going to go back and now talk about proving that the nth cyclotomic polynomial has integer coefficients. The goal for the rest of this video is to prove that the nth cyclotomic polynomial has integer coefficients. And there are a couple of ideas that go into this. The first one is that we're going to argue by induction on n. Okay, n equals 1, check, x minus 1 has integer coefficients. So we're going to assume that the dth cyclotomic polynomial is in z bracket x for all d less than n. And there's this other idea that is we're going to use some facts that we know about division in polynomial rings. So I want to take a little time with this one because it's easy to forget exactly what we know. So this is something from section 9.2. This is on page 301 that we talked about in Math 206b. If you have 2 polynomials, a of x and b of x in f bracket x, then the quotient and remainder in the division algorithm applied to this pair of polynomials is independent of field extension. All right, so what does that mean? In f bracket x, there exist two polynomials, q of x and r of x, in f bracket x, such that a equals q times b plus r, where either r is 0 or the degree of r is less than the degree of b. And more than just these polynomials exist, but they are unique. So starting from a and b, we get a unique q and r. So now suppose we're in this situation where E is a field containing f. We can take the polynomials a of x and b of x and think of them as elements now in E bracket x, this larger field bracket x. By the division algorithm in this field E bracket x, there exist capital Q and capital R elements in E bracket x such that a equals q times b plus r, where r equals 0 or the degree of r is less than the degree of b. But these q and r that we got before, these polynomials in f bracket x, you can think of them as elements in E bracket x, and they satisfy this equation. Right? We have a equals q times b plus r. So by the uniqueness of the quotient and remainder in the division algorithm in the polynomial ring over a field, this element in E bracket x, q, is the same as this q we had before, and this new r is the same as this r from before. So one special case of this is that b divides a in E bracket x if and only if b divides a in f bracket x. This is the fact that we're going to use in showing that the cyclotomic polynomial has integer coefficients. So let's keep this in mind. I'll pause and erase and continue with the proof. We know that x to the n minus 1 is equal to the nth cyclotomic polynomial times a product over all divisors of n, but d less than n, d not equal to n, of the dth cyclotomic polynomial. So we've taken this factorization we have from before, and we've just pulled out the one special term, phi n of x. So let's group everything else together. And it's clear now that x to the n minus 1 is phi n of x times f of x, this product, where f of x, it has integer coefficients because each thing in this product has integer coefficients. And it's monic because each thing in this product is monic. So now we're going to apply this result that we were just talking about. We see that f of x divides x to the n minus 1 in q adjoins zeta n bracket x, that f of or x to the n minus 1 equals f of x times some polynomial that's in q adjoins zeta n bracket x. But by this result that we were just talking about, f of x divides x to the n minus 1 in q adjoins zeta n bracket x if and only if f of x divides x to the n minus 1 already in q bracket x. That because x to the n minus 1 and f of x are both in q bracket x, by this uniqueness of the quotient and remainder in the division algorithm, f of x already divides x to the n minus 1 in q bracket x. That means x to the n minus 1 equals f of x times some polynomial that's in q bracket x. So this shows that the nth cyclotomic polynomial has coefficients in q. But that's not exactly what we're trying to prove. We're trying to prove that, in fact, the nth cyclotomic polynomial has coefficients in z. So there's one more idea that goes into showing this, which is we want to apply Gauss's lemma, proposition 5 in section 9.3. This is something we haven't talked about recently at all, so I want to recall what it says in this setting. If we have a polynomial p of x that's equal to capital A times capital B in q bracket x, so it's a product of two polynomials with rational coefficients, p of x, this polynomial, has integer coefficients. So we have some polynomial in z bracket x that's equal to a product of two polynomials with rational coefficients. Then there is a non-zero element r in q such that r times capital A is some polynomial little a of x that's in z bracket x, and r inverse times b of x is equal to some polynomial little b, which is in z bracket x. So you have some polynomial with integer coefficients, and it's equal to a product of two polynomials in Q bracket X, then there's a way to scale one and scale the other so that it is equal to a product of two polynomials, each of which has integer coefficients. So P of X equals little a of X times B of X in Z bracket X. Factorizations in Q bracket X give you factorizations in Z bracket X. Okay, so how are we going to apply this result? Well, what do we have? We have x to the n minus 1 equals a product of two polynomials that, okay, f of x is in Z bracket X, but we don't know. The nth cyclotomic polynomial might be in Q bracket X. So what Gauss's lemma says is this integer polynomial, we have this product of polynomials in Q bracket X. There exists a non-zero r in Q star so that r times the first polynomial is in Z bracket X and r inverse times the second polynomial is in Z bracket X. But these two polynomials, these are two monic polynomials. So if we scale one of them by 2, we're going to scale the other one by 1/2. And whichever, if we scale one of them by a rational number that's not an integer, then the lead coefficient is now going to be this rational number that's not an integer. So the only possibility of an r that we can multiply by r times the first, r inverse times the second, such that we get two things with integer coefficients, just because the lead coefficients have to be integers, we see that the only possibility is r equals 1. Or I guess r equals -1, but then if you multiply each of these by -1, you can cancel them out. So what are we seeing? There exists this r in Q star such that r times the first polynomial has integer coefficients, r inverse times the second polynomial has integer coefficients. Okay, the only possible r is r equals 1, which means that the first polynomial and the second polynomial already had integer coefficients. So an application of Gauss's lemma shows that this factorization that we have for x to the n minus 1 in Q bracket X shows that this was already a factorization in Z bracket X. And cyclotomic polynomial has coefficients in Z. This completes the proof. So what really happened in this argument? There were a few key ideas. First, induction on the degree, which let us write x to the n equals the nth cyclotomic polynomial times something that had integer coefficients and was monic. We have this result about how the quotient remainder in the division algorithm is independent of field extensions, which showed that that because this f of x divided x to the n minus 1 in Q adjoins zeta n bracket x, it already had to divide x to the n minus 1 in Q bracket x. That shows that the nth cyclotomic polynomial has rational coefficients, and Gauss's lemma shows that in fact it already had integer coefficients. So what do we have left to do? In the next video, we'll prove that the nth cyclotomic polynomial, it's this monic polynomial of degree Euler phi of n with coefficients in Z, and we'll show that it's irreducible, which means that it is the minimal polynomial of zeta n, a primitive nth root of unity, which gives us the degree of the nth cyclotomic field as an extension of Q.